Couldn't turn the music on then. All right. I said this was the last one, but this is the last one on vectors. And this example is so important that we're essentially going to do it and then make up another one. And this is what we're going to do in class. We're going to make these up all the time. This is the cream of the vectors crop, shall we say. This will almost certainly be on your exam. That's not why we're learning it, but it will almost certainly be on there. They love it, and kind of, again, it really does test your understanding of what's going on here. So let's go for this. This is really important. So a vector line L goes through the points A and B with position vectors, blah, blah, blah. So we should be very used to and very comfortable now. Just be careful, that's minus 4k, and there's no j, all right? So be careful. We should be comfortable with constructing line equations now. A vector line goes through that. So R is going through A plus lambda A to B. So that's B subtract A. Minus 2 minus 3 is 5. 3 minus 0 is 3. 2 minus 4 is 6. There's your line. And it also says a point C has position vector 6, 4, minus 9. Find the point X on the line such that L and CX are perpendicular to each other. That sounds hideous, doesn't it? And with vectors, without a picture, I can't even look at you or talk to you. If you haven't drawn a picture, it would just be like, have you drawn a picture? No. Well, I won't talk to you then, because I can't work this stuff out without a picture. It's really hard to visually see what's going on. So let's just draw a quick picture. Let's always put an origin there. Really important when we're having vector pictures. Always an origin. Here's our line, AB. All right. And it's saying that C has position. Let's put that in there. So A and B. There's our line. There's A. There's B. Yeah. And it's saying there's a point C, 6, 4, minus 9. I could check. I could verify. Is C on the line? Is C on the line? Well, let's do it actually. Let's pretend the question says, ask if is C on the line. So if C on line. Therefore, remember, R is any point on the line, so if C is on the line, therefore that constitutes a point. So 6, 4, minus 9 would equal the line itself, wouldn't it? And remember, lambda is the scalar. That's a number, that's a constant, so it remains constant. So it must work for top, middle, and bottom. So I can see straight away that the top line, 6 take 3 is 3, divided by minus 5, lambda is minus 3 by 5. Can you see? Middle line, lambda, is 4 by 3. Straight away these two are different, and therefore C can't be on the line, can it? It can't be on the line if you've got different values of lambda. So there's our quick verification that C is somewhere else. I don't know, C could be here. Let's make it up. Remember, our pictures can help us. We can use artistic license all we want, because it just helps us visualize what's going on. So it says find the point X on the line, so X is on the line, such that C to X and L, the line, is perpendicular to each other. This is our line L, isn't it? So we're saying C to X, there's a point X where C to X is perpendicular to the line here. How do we translate that into maths? What do we know about the dot product, about perpendicular dot products? If perpendicular, if X and Y are perpendicular to each other, we know that the dot product is 0, don't we? That's going to help. That theory is going to help. Let's think about it. Let's translate what we've got here. We're saying that C to X dot. Now, what can we use for the line? What is the line? What's the direction of the line? You see what I'm saying? The direction of the line. The direction is the direction vector. And the direction vector is a to b. Do you understand? You're comparing this vector a to b with c to x. So a to b, or the direction vector. We know that this is 0, and therefore we can exploit this fact and start working this out. So what is c to x? What is x? Well, x is a point on the line, which we don't know yet, do we? We don't know what x is, but we know x is a point on the line. R is a point on the line, isn't it? Any point on the line. So if x lies on the line, then x must be the same as r. That's the thing. That's the key bit of understanding that you either get or you need to work to get. X is a point on the line. We don't know what it is, but lambda could be anything, and x will be a specific value of lambda, right? That's x. We know what c is. We know c is 6, 4 minus 9, and therefore we know what c to x is, don't we? C to x, last thing minus first thing. So I've got 3 minus 5 lambda, 3 lambda, minus 4 plus 6 lambda, and now take away our c. So take 6, take 4, take away minus 9. Dot a to b. We already know a to b is the direction vector. So minus 5, 3, and 6. And this all equals 0. Right? Why have we done that? Well, let's clear this up. So 3 minus 5 lambda minus 6. So that's minus 3 minus 5 lambda. 3 lambda take 4. Minus 4 plus 9 is going to be 5, isn't it? Minus 5, 3, 6 equals 0. How do you do the dot product? Top times top plus middle times middle plus bottom times bottom. So minus 3 times minus 5 is 15. Minus 5 lambda times minus 5 is plus 25 lambda. Plus 3 times 3 lambda is 9 lambda. Minus 4 times 3 is minus 12. Plus 6 times 5 is 30. 6 times 6 lambda is 36 lambda equals 0. Do you see why we did that? Because now we have one unknown, lambda, and it all equals 0. So now we can find lambda, can't we? Add all the lambdas up. So we got 25 plus 9 plus 36. So I've got 70 lambda here equals. All the numbers can go on the other side. So that's going to give me minus 33 if I move that all over. So therefore lambda must be minus 33 over 70. So you're not going to get nice values for lambda. They're always going to be horrible. Okay? Well, not always, but quite a lot of the time. It wants us to find the point x, remember, so we're not finished. We know what x is. X is here. So now we just need to sub in that value of lambda. So that's minus 33 over 70. 3 minus 33 over 70, and we got minus 4 plus 6 times minus 33 over 70. So this should be horrible numbers. Minus 33 divided by 70. So 3 minus 5 answer. 75 over 14. 70 times by 3. Minus 99 over 70, minus 33 divided by 70, times 6, minus 4, minus 239 over 35. Hopefully I haven't made any mistakes there. If I have, just let me know. And that's essentially it. And you'll see now how we can just make up another one. Let's make up another one and make sure we've got it. So let's say this time x is 312 and y is 421. See, I'm just making this up. And let's say there's an external point t with coordinates 1, 0, and 2. And the question wants us to find the distance, the shortest distance of t from the line going through x and y. So let's do it. Draw a picture, always helpful. There's x, there's y, there's the origin, vector x, vector y, external point t, don't know where it is, could verify if it's off the line, I hope it's off the line. So find the distance of t from the line. You know that there's a point on the line, we can call it anything we want. Let's call it z. Right? I want to find the distance from t from the line, so therefore it must be the perpendicular distance. That's always the shortest distance, isn't it? So same again. I want to find an angle between them, and I know that angle is 90. So t to z dot the line, the whole line. Not interested in the entire line, am I? I'm just interested in the direction vector, and the direction vector is x to y equals 0, right? So you see, I don't actually even need the line equation necessarily until I start piecing my things together. So what is z? Well, z, as we said before, is any point on the line. So this should straight away get you to go. Z is x plus direction vector times by lambda. Direction is x to y, so that's y take x. So 4 take 3 is 1, 2 take 1 is 1, 1 take 2 is minus 1. So therefore t to z is going to be z take t. So t to z is 3 plus lambda, 1 plus lambda, 2 minus, oops, 2 minus lambda. There's your z. Take away the t, so minus 1 from here, minus 0 and minus 2. And this is all dot xy, and xy, as we said, is that direction vector equals 0. So therefore, let's clean this up. 3 take 1, 2 plus lambda, 1 plus lambda, 2 take minus 2 is 0. Dot 1, 1 minus 1 equals 0. So now, dot product, top times top, 2 plus lambda, plus middle times middle, 1 plus lambda, plus minus 1 times minus lambda equals 0. So I hope I haven't made up one which falls on the line. So that's going to give you 3 lambda on the left equals minus 3 on the right. And therefore, lambda must equal minus 1. Lambda plus lambda, yes. And now we can sub that back in because we're trying to find, well, we're trying to find the distance of t actually. We're not trying to find that point x this time, or the point z here. So first we need to find the vector t to z, don't we? And then find its magnitude to get that distance. So t to z, we already calculated, was this one, wasn't it? This is t to z, so 2 plus lambda. So t to z is 2 plus minus 1. 1 plus minus 1, and minus times minus 1. So that gives me 1, 0, and 1. So therefore, the shortest distance is that magnitude. So that element squared plus that element squared plus that element squared. So we get root 2. And we're finished. That's it. We will do something else in class. So that's essentially the essence of it. But there will be a lot more challenging stuff in class.